Hi, folks. I hope everyone can hear me. So today's talk is about Yarn Federation. So this is to scale Yarn to 100,000 nodes and beyond. So this is work done at Microsoft by two teams. The one team is the Cloud and Information Services Lab, this is CISL. So this is an applied research team, which mostly we deal with large-scale systems and distributed machine learning. And the second half of the team is the Big Data Resource Management team. So we build, design, and operate all the shared compute big data service for all of Microsoft. So all of the folks are here right at the front. So if you want to catch up after the talk, they're here. And I'm Subru. So I'm a research engineer at CISL, and I've been a contributor to Hadoop since 2008. So we have a short and sweet agenda here. So I'll start with talking about Yarn at Microsoft. This is relatively new and quite happening space. I'll hand over to Kishore, who will walk you through the Federation architecture. And as you will hear from Kishore, you will see that the architecture opens up a lot of interesting policy space, which Carlo will walk you guys through. And we saved the best for the last. We have a demo. So this is just to say that we didn't just draw boxes to get a free pass to the Hadoop Summit. We do have something working, right? So yeah. So most of you guys have been working around with Yarn, so you're familiar with the challenges. Like, how did Yarn come about? The major reason was ability to support the diverse workloads, right? So Hadoop v1 supported MapReduce natively, but that's it. But with the systems coming with Hive, Spark, Impa, all of those systems coming into the world, you need to support not just batch, you need to support interactive queries, long-running services. You have heard a lot about this in previous talks yesterday by Vinod, Wangda, and folks. So that's one of the reasons. And then you want to support production SLAs, right? So, and this becomes more challenging when the workload diversity increases, right? And clusters are pretty expensive pieces of hardware to buy and operate. So you want to make sure that you get ROI on your clusters. That's the utilization, right? And this, on top of all of this, we have some special challenges which makes it a little more fun in Microsoft. One of the things is we've been doing big data at Microsoft for close to the last decade. So we want to leverage the existing infrastructure. So we just don't want to throw it away, we want to build on it, right? So this is the Cosmos scope. So if you guys have either read the Apollo paper, the scope paper, or have you guys tried out the Azure Data Lake Analytics, it's that. If you don't, there's an opportunity, go try that. And we have Azure, we have the Azure infrastructure, right? So we want to use it. And we have other stuff which is also contributing to Apache like Reef, which enables distributed machine learning, right? So we want to, and on top of this, using our existing strong infrastructure, we want to open up the rich open source ecosystem. So this is the giraffes, the Sparks of all the world, so that people essentially want to bring their own job. That's the model, right? So you can't tie people to say, just use this model. People want to bring their own job. So we want to enable that. And we want to do this at the scale of the Microsoft clusters. And no surprises. So we have Bing, Office. These are the gigantic systems in the world. So our clusters today exceed 50,000 nodes, many of our clusters. So to be future-proof, we want to be, at least say that, we want to scale our system to 100,000 nodes and beyond, right? And the last, and which makes it even more, the last twist, which makes it even more interesting is, we want to do this not just for on-premise, so a solution which just works for on-premise, but we want to make sure it works for a public cloud, because we have a huge public cloud offering with Azure. And what does that mean? So we have the challenges of multi-tenancy, security, integration with services, right? So when we have all of these challenges, we had a lot of brainstorming. What we decided is, we decided to take a big bet. We said that we're going to have a unified resource management for all of Microsoft Big Data, and this is going to be based on Yarn, right? So what does this mean? So as all of you are aware, Microsoft has been pioneers in open source. Not really. So what we decided is, like, let's make a conscious decision. We are not just going to take Yarn and then muck around with it and deploy it, do all of this stuff. We are going to innovate and contribute whatever we do on Yarn, right? So we're going to be part of the Apache community. And to give some examples, some of the stuff which we've been driving, this is like going back to the previous slides. One of the stuff, first thing we did is, like, we wanted to add SLAs for production job. So this is, we built a reservation framework in Yarn. So it's called Rayon. So what it does is, you can now specify a skyline of resources with a deadline. So you say, suppose I want 100 containers from 2 p.m. to 3 p.m., and then I want 400 containers from 3 p.m. to 4 p.m. So this is what my production job looks like to make sure I meet the deadline. So we have added this ability to Yarn. It's available from Hadoop 2.6. It's been in preview, and 2.8 is where we are going to call it a general availability. So this is Rayon, and we did a talk about this in the last Hadoop Summit. Yeah. So another aspect is the ROI on the clusters. We want to make sure the utilization of the clusters is good. So, and here one of the aspects is we have ginormous jobs which have a lot of short-lived containers. So in Yarn, as you are aware, you have the heartbeat asynchronous latencies, which are okay if your containers, it gets amortized if your containers have some execution which is manageable, but if you have very tiny execution, this causes a problem. So what we wanted to make sure is we wanted to mask the latency of the asynchronous heartbeat. For that, we did a couple of things. We added node level queuing, so that you have tasks as node immediately queued, so you can start executing them. And we introduced the notion of container types. So this is something which Jason talked about yesterday in the oversubscription, because this is not, we are also going to use this with the oversubscription work which is happening. So this is Yarn 2877. So we also had a talk about this last Hadoop Summit, and this is a very freshly minted feature. We're hoping that we'll include this, have this as part of 2.9. So there's still some work to be done, so welcome to contribute there. And coming to the point of today's talk, right? It's what we are trying to address here is Yarn scalability. So as we mentioned, you're going to hear again and again, we want to be able to scale Yarn to 100,000 nodes, right? So what we are proposing here is Federation. So think of it like we want to stitch together Yarn clusters. So think of it like what two design principles we are following here. One. Yeah, I'll just continue to hopefully, yeah. So we are trying to follow two design principles here. One is to make sure that this is, the Federation work is transparent to the application, so that application need not have to have code change or even recompile, right? So if you want to change application code to have new features, that actually makes an entry barrier, which is not easy. So we want to make sure it's completely transparent to applications. They just get a larger cluster to play around. Another design principle which we followed is to make sure that we reuse all the Yarn innovation which is happening in Yarn, right? So we are building on the Yarn clusters, and we are also contributing there, so we want to make sure we also get back the benefit. So that's the second design principle we're following. Okay, yeah, so yeah, let's just, so yeah. So what we try to do here, Kishore will go into more details, is like we tried a very simple thing, is like a layer of indirection solves all problems in computer science. That's kind of the approach we have taken. Kishore will talk more about it. And this, for people in the audience who have 100,000 nodes to run Yarn, I know you're all pumped up to hear more about this. But for people who don't, there's still use for Federation. There's a couple of other interesting use cases for Federation. One is everybody who has Yarn in your companies don't have just single cluster. So you have a lot of clusters. This causes fragmentation issues, right? So you have varying patterns on your clusters. So we have clusters, some of which are heavily utilized during the night, some during the day, some during holidays, some during work days. So you want to pool in clusters, right? So that you get to bump up your utilization. So that is a private cloud concept, right? So that's what we call as private cloud. So this helps for people who have a lot of small clusters even, or even a few small clusters, right? Another interesting thing, which is, we just started looking into it, and it's having very initial results are very extremely promising, is using this Federation architecture to do cross data center data processing. So take the example of Skype. So we have users of Skype across the world. So the promise of Hadoop initially was take compute to where data is, but as long as the data is in one data center, right? So when your data center is spread across the world, you ended up copying the data through the costly vans into your data center and then run analytics there. So with Federation architecture, you could think of a federated query running actually where, pushing compute to where data is and running in the local data centers, right? So this is one and a very interesting use case here. Okay, so where does Yarn Federation, all of this stand in Apache, right? So we have an umbrella JIRA. It's Yarn 2915. So we have put up a detailed design proposal there, and we have an end-to-end patch to just show things, how things work. We have created a branch because obviously it's a large, non-trivial feature, so we're going to do a branch development. So we've created the branch, and the API patches are just posted. So As you can see, this is a great time for people to come in and contribute. There's a lot of work to be done. So we have already few folks have been contributing, so I just want to call out, so helping especially the design and iterating to get to this stage. So it's Vangda, Karthik, Vinodji, and the rest of the folks. So now I'd like to introduce Kishore. So like we said, we made a big bet on a unified resource management team. So Kishore is the engineering lead for the team, and he'll walk you guys through the Federation architecture.
Thank you, Subru, for the introduction. Good morning. Today I'm going to give you an overview of Yarn Federation architecture. But before that, let me restate a statement which Subru just made. He said, applications can scale to hundreds of thousands of nodes using Yarn Federation. That's right, hundreds of thousands of nodes. Sounds unrealistic, right? But it works. It's amazing, it's just beautiful to see applications when they scale to this level. As you know, in Yarn, the resource manager is a single instance. So no matter what you do, what kind of hardware you use, what tweaks you add, there will be a point at which it will choke. The scalability of Yarn is affected by several factors. It's affected by the number of nodes, the number of applications, the number of tasks which run in the cluster. It depends on the heartbeat interval of node managers and the applications. It depends on the task duration, the type of workload which runs on the clusters. For example, in Microsoft, we have seen that some of our workloads, these are huge jobs which run for several hours continuously. They launch hundreds of thousands of containers which are very short-lived. Now, when I say short-lived, I'm talking of order of seconds here. These containers launch, do their work, and go away in few seconds. Such kind of workload puts a tremendous amount of pressure on the resource manager. Now, we know that Yarn is battle tested, on 4,000 to 8,000 nodes inside Microsoft and in several other companies. But at Microsoft, we have clusters which are more than 50,000 nodes, and we have several of those. With the current architecture of Yarn, it would be very difficult for us to scale to that level. That is why Yarn Federation was born. It was born so that we can run Yarn on Microsoft production clusters. So how does Yarn Federation actually work? How does it enable applications to scale to that level? What is the magic? What is the secret sauce here? Let me show you how. Assume what you see here is a data center with large number of machines, hundreds of thousands of servers. The first thing we do is we deploy Yarn on them. We deploy multiple instances of Yarn cluster. We call them Yarn subclusters. These subclusters are just normal Yarn clusters with around 5,000 to 6,000 nodes each. And they don't know about each other. They are independent and isolated. Next, we stitch them together using a layer of federation. We stitch them in such a way that for the clients and the applications, they all look like one huge Yarn cluster. How does that happen? Let me take an example. Let's take an example of a client trying to submit a job. In classic Yarn, the client would directly connect to the resource manager and submit the application. But in Federation, it talks to a new service called as router. The router implements the client RM protocol. So from the client point of view, it still thinks it's talking to the resource manager. The router is a very simple stateless service, and if you want to scale it out, you can add multiple instances of the router and put it behind a load balancer. When the router receives the request for submitting the app, it looks at a policy to determine the subcluster where this message should go to. This policy is a pluggable piece of software which you can write and plug it in using configuration. Ultimately, the policy decides, it makes the decision where this request should be routed to. The router follows the order and then it submits the request to the resource manager of the selected subcluster. The resource manager launches the application master and the application starts. So far so good, pretty straightforward. I am going to move this application master out so that it's easy for me to explain. I am going to talk about one of the secret sauces in the Yarn Federation architecture, and I don't want you to miss it. In classic Yarn, an application master again would connect to the resource manager, register itself, send heartbeats and ask for containers. But in Federation, it talks to a new per node proxy called as AMRM proxy. As the name suggests, it implements the AMRM protocol. So from the application point of view, it thinks it's talking to the resource manager, not knowing that it is talking to a proxy which is running on the same node. When the application master sends registration request, the AMRM proxy forwards it to the home RM. Here, when I say home RM, that is the RM which launched that application. Next, when the AM sends heartbeats and asks for containers, the AMRM proxy looks at the policy again to decide where these containers request should land. Again, the policy finally decides, and AMRM proxy just connects to the resource managers of the selected subclusters. The AMRM proxy negotiates containers on behalf of the AM, aggregates it and returns it back to the application master. Once it gets the containers, the application master directly talks to the nodes, the node managers, and launches the tasks. And voila, you can see here that the application has transparently spanned across multiple Yarn clusters and scaled to data center level. It's amazing. Now, as I told you, this AMRM proxy is one of the secret sauces. There is a lot of work which is done in this proxy which helps with the Federation. I want to double click on that and show you exactly what's happening inside. The AMRM proxy is just a new service we added as part of Federation. It is hosted in the node manager. It has one endpoint, and that endpoint implements the AMRM protocol. The application master is configured to connect to this endpoint rather than the real resource manager. When the application master connects to the AMRM proxy, it instantiates a pipeline inside. One instance of the pipeline is created per AM. So if you have 3 application masters running on one node, there will be 3 distinct pipelines. The AMRM proxy was designed with extensibility in mind. So the pipeline is nothing but a collection, a chain of interceptors. You can write your own interceptor and plug it in using configuration. In our case, in Microsoft, we have more than one interceptor running all the time. The first interceptor in the chain is called as the security throttling interceptor. Its job is to make sure that nobody attacks RM. It prevents DDoS attacks on the resource manager. So why do we need it? We deploy this software on our public cloud, and most of the time the applications which run have user code which is not written by Microsoft. So an hostile application can attack the resource manager and bring down the cluster. And this interceptor makes sure that doesn't happen. Now, when the federation is enabled, the last interceptor which gets plugged in is called the Federation Interceptor. The bulk of the work for federation is done here in this interceptor. When the application master sends container requests, the Federation Interceptor uses the policy, it determines which subclusters it should go to. Then it registers itself as an unmanaged application master to the resource managers of the selected subclusters. The unmanaged application master negotiates the containers, aggregates it, and returns it back to the AM. And the rest you have seen. So, as you can see, the design is very simple. The implementation is very small. There is few lines of code, but it delivers a feature so powerful that it enables applications to span across multiple subclusters and scale to data center level. Cool, huh? Next, so I mentioned about the policies which are used by the router and the AMRM proxy service. Carlo Curino, who is a scientist in our group, is going to deep dive and give you more details about the policies and how it is used in Yarn Federation. Please welcome Carlo.
Thank you, Kishore, for the introduction. I think we're running a little long on time, so I'm trying to catch up a little. So Kishore told you about the secret sauce. Now I'm going to tell you about the secret spices that we use to make the secret sauce. Please take notes. I'll start by underlying one aspect, right? In our design of federation, we built several components. We have the router service on one side, we have the AMRM proxies, we have all the schedulers running each one of the RAMs. These components act as sort of general purpose enforcement mechanisms that follow the policy. Like, we centrally define a set of policies, and by coordinating the behavior of all these components, we will affect the overall behavior of our system, right? Now, one thing we didn't tell you yet is like how the policies show up there, right? How do we put them in there? So I'm going to introduce another component. It's called the policy engine. These behave similarly to the router service. It's a stateless component. It runs as a service. And in first approximation, or in our first design, exposes a federation admin API. This is an API that an operator can use to manually curate the set of policies. For now, everything manual. We're deciding manually what the router should do, what the AMRM proxy should do, what each of the RAMs should be doing to route job, route requests, and so on and so forth. But in the fullness of time, our design is such that the policy engine should play a more active role. It will be able to observe the state of the system and dynamically make decisions and tune and tweak the policies to best serve the objectives that we have in this cluster. So now, all of this policy game, right? We built a lot of infrastructure. We describe a lot of it. Like, why do you care about all this? Like, there's a lot of flexibility you're building into the system, and maybe are you over-engineering it? Well, the point is, our goal is to efficiently operate a large federated cluster. Turns out that no one has done it yet. So we don't have exactly an idea of what's going to happen, right? We don't know exactly how each one of the components will behave, how jobs will route it, the load around, right? And most importantly, as Suburo mentioned early on, there are different applications of federation, different deployment scenarios for which we want to use federation. In some scenarios, we might just want to use it for fault tolerance, just a way of falling back. If an entire subcluster is down, we're going to fall back on another one. Or maybe we want to use it to isolate tenants, literally physically running different jobs in different subclusters so that the nodes they use are separate, right? So they don't bother each other. Sometimes node labels are used for something similar. And in other cases, we just want to run an absolutely huge job, or running on a large number of jobs on many subclusters, and load balance all of them, maybe trying to guarantee global fairness, even if we have distributed enforcement mechanisms, right? So by being very dynamic and very agile in tweaking our policies, we'll be able to explore this space and kind of learn how the system works at this unusual scale. So what do policies look like? Well, policies receive an input, a set of information about the request being made, right? So, for example, they know what user is submitting a job submission request, what are the reservations that the user has, which queue is being submitted to, maybe the node labels that the job is intended to run on. And of course, resource requests, so we're going to know the locality requirements, the size of containers, how many containers. So this is the input that they receive. But they also have a bunch of information about the state of the cluster. So they maybe know what is the current load in the different subclusters, or the fact that we have planned maintenance for subcluster 3 that is going to go down at 3 o'clock, right? And based on this, they will make a set of routing and scheduling decisions in different places of our architecture that, when all combined, fully determine where every single container allocation happens in the system. So this is all very abstract, right? It's very high level. So let me try to show you one specific hard problem and how we use policies to try to solve it. So one of the things we are aiming with Federation is to try to be transparent to applications. Well, also we want to be transparent to operators. So ideally, we want to give you the illusion of a single global queue structure. But now it turns out that we have local enforcement, right? We have several RMs. So how do we map this global queue structure into different RMs? And I'm going to show you how we use properly tuned policies to affect this. And it turned out there is a spectrum of options that we can play here. So at one extreme, we can say, well, let's just full partitioning of this queue structure. We're going to take subtrees and we're going to map them to different subclusters, right? The router and the YAML proxies is a very simple job, as policy goes. They're going to receive a request. They're going to look up what's the corresponding queue and where the queue is mapped to, and just going to connect to that RM and forward all requests there. Pretty simple. And it turns out that that is good to give us perfect scale out, right? We have hard partitioned the workload. We have hard partitioned the nodes. Each one of the subcluster operates almost independently. And so we can scale to 1 million nodes, no problem. And we do this with actually good isolation, right? Different users or the users that belong to different queues will be completely physically isolated, right? They run on different nodes. Of course, this is not ideal for other aspects, right? In terms of fragmentation and utilization, well, if jobs in QB are not fully utilizing their resources, the other guys cannot really leverage the leftover space, right? So fairness also is kind of hard to accomplish there. Also, the maximum size of a single job that we can run is now bounded by the size of a subcluster. And if one of the subcluster goes completely down with all their MHA, doesn't keep it up, well, now we have an uneven impact of the missing capacity to our customers, right? So this is good for some scenario, not for all. Well, let's look at the opposite side of the spectrum. Let's just say we do full replication. We take the queue structure and we map it in each one of the subcluster. And now we tell the router, whenever you receive a job, just round robin or randomly pick one of the subclusters to start the job. And when the MRM proxy is forwarding resource request, it's going to look up the locality in the request, send it to the subcluster that have those nodes. And if the request doesn't contain locality, it's just an any request, we just broadcast it to all nodes. OK, this is also very simple, which we like. It's very symmetric. And it gives us for free fairness, and it gives us for free resiliency, right? Anything goes down, it's OK. All the rest of the subcluster can take the load, right? So we have a nice set of properties. But now the scalability in number of jobs becomes a little hard, because every single resource manager will be seeing all of the jobs potentially in our federation. So it's hard to scale in the number of jobs we run. Now, it turns out we have a bunch of heuristics that we can apply in these cases. And if you're interested, we can talk offline about those. But let me tell you sort of the point of tendency. This is the dynamic partial replication, right? The idea is to say a queue is not mapped to a single subcluster, is not mapped to all of the subcluster, but is to map to a subset of the subcluster. Now, if we choose that subset carefully, we can take the advantages of both the partition and the replication strategies. We'll be able to scale a single job to many, many subcluster while not having every job talking to all of the RMs, for example, or getting some isolation for some tenants that really don't want to be bothered by anyone else. Now, this, of course, is hard, right? It's more complex. We need to dynamically, potentially rebalance it over time. We need to observe the state of the system. And this is why I'm describing it as sort of a point of tendency. And it's more in the world in which the policy engine will be a very active component that does things sort of dynamically. So with this, I would like to introduce what we're going to do in the demo. What Giovanni is going to show is a basic job running across multiple subclusters. It's going to be an unmodified application. We're going to show you a UI and some ops command, nothing fancy, but the basic stuff that someone running a federation might want to be able to look at. And the policy we're going to show is a user-based partial replication, right? So Giovanni will show manually how he can map a single user to a different set of subclusters. So this might be a way of isolating different tenants. With this, I leave to Giovanni. Please switch to the demo. Giovanni is a research engineer in the big data team at Microsoft and one of the core developers behind Federation.
Hi, everyone. So thanks, Carlo, for the introduction. So today I will present you our demo of the first version of Federation. So this web app runs inside the router. Router stitch all together the information from subcluster and give to the user one single view of all this information. So as you can see, the first column is about subcluster identification. So in this federated cluster, we have 8 subclusters. The next 5 columns represent the number of applications submitted, running, completed, failed, and killed. The next column is about how many containers are running in that exactly moment and how many active nodes are in each subcluster. So about nodes. At the beginning, I want to go with 100,000 nodes, as my coworkers said before, but then I decided not to take over the entire production for a little bit demo. So, first of all, as Carlos said before, this is, the job that I'm going to run is use a user-based policy. With this command, I set for Hadoop user to run across all the subcluster. And I'm going to run a MapReduce job from distribution 2.7.1. This is a modified application. I'm going to start. Okay. So in the router view, we add also an application web page. This is similar to the Yarn RM web page, but at the end, he's also summarized the number of subcluster that is running on. So as you can see, the router picks subcluster 4 to start the application number 1. But as soon as start going to run, he span across all the subcluster and get containers in all of them. Okay, the job is almost completed. I'm going to run the same command of before, but I'm going to reduce the number of subcluster, and my user can run only in the first 2 subcluster. The application is completed. I'm going to run the same one. Okay. In this moment, the application has to start soon, and yes. Yeah. In this scenario, instead, router picks subcluster 1 to start the application, but as soon as possible, he span across this first 2 subcluster. Runtime, I'm going to add a new subcluster for my user, and as soon as I change the policy, the IAMRM proxy picks the new policy and spread the application number 2 over subcluster 3. And as we can see from here, he fill up all the resource. And in subcluster 3, we have the presence of a federated unmanaged EM. That is a normal application that only requests resource, but the main guy run inside the cluster. Okay, so in Federation we work with multiple subcluster. So another cool feature that we add is bring an entire cluster in a maintenance mode. With this instruction, I bring the subcluster to draining, and I give 100 second time slot. What does it mean? At this point, the RAM stop to accept new application and allocate new container. And after 100 seconds, he killed the remaining running container. So what I'm going to do is run the third application, again the same one. Yeah, I'm waiting now. I mean, while the application starts, I want to show you guys the nodes web app that we add in the router. This is the same one that we can find in YARN RAM, but he has also in the first column the subcluster in which is belong. The application start in subcluster 1. As you can see, application number 3 start and running over these 3 guys. Runtime, I'm going to bring the subcluster down for maintenance. None of neither container are running, so the RAM go into maintenance mode, and we can do all the operation for maintenance. So with this one, I conclude my demo, and as my coworkers said before, in the next few weeks, we are going to contribute under YARN 2915. You are willing to give us feedback and also help us to contribute. And we are willing, if time is concerned, we are willing to get question, otherwise offline. Thanks.
We can take a couple of questions.